Number 8. On table 3, on page...
Ooh, not 155, guys. It's actually on page 145, guys.
So table 3 on page 145 of the text lists successive ionization energies of several different elements. A. Identify the electron that is removed in the first ionization energy of magnesium. Well, magnesium inhabits the 3s2 position.
And so the very first electron that's going to be removed is 3s2.
Identify the electron that is removed in the second ionization energy of magnesium. Well, once we remove one of the 3s electrons,
We only have one left. So that's the 3s1 electron.
now once we move that, we will have reverted back to our noble gas electron configuration that is equal to neon. The same electron configuration as neon. And so the highest energy electron we'll have
Then is, see where we at?
2p6. But we'll have 6 2p electrons and 2 2s electrons. We'll have 8 valence electrons. We'll have an octet. We'll be stable. We'll be nice and strong. But C, identify the electron that is removed in the third ionization energy of magnesium. Well, that's going to be
The 2p6
electron, because it's now the highest energy electron that's in the system. And you'll see by looking at that table that you'll see the data that you need to answer D, which is explain why the second ionization energy is higher than the first, the third is higher than the second, and so on and so on and so on. Well, as electrons are removed in successive ionizations,
right? We remove the
3s2 electron, then the 3s1 electron, then the 2p6 electron, okay, on and on and on. And we can only remove one electron at a time. It's not like we're ever removing 2 at a time or 3 at a time. But as electrons are removed in successive ionizations, fewer electrons remain within the atom, obviously, to shield the attractive force of the nucleus. Remember, the nucleus is positively charged, and the electrons are negatively charged. They want to fall in towards the nucleus. The only problem is, as they fall closer in towards the nucleus, they actually have to get closer to one another. The electrons, all being negatively charged, are supposed to fall in closer to one another. Well, there's a balance between getting closer to the positively charged nucleus and staying further away from the other negatively charged electrons. So as we remove more electrons, there are fewer electrons within the atom to shield the attractive force of the nucleus. Each electron removed, okay, as we keep on going, each electron removed in successive ionizations experiences a stronger effective nuclear pull than the electron removed before it. Every single time I remove an electron, the effective nuclear charge increases.
right?
Effective, the nuclear pull that's actually affecting those electrons out there, becomes stronger because there's less shielding. So every time you remove an electron, you decrease the amount of shielding. Each time you decrease the amount of shielding, you increase the effective nuclear pull. And anytime you increase the effective nuclear pull, that means those electrons are being held more and more tightly. And if at any point you're holding on to an electron more and more tightly, it's going to take more energy to remove that electron. That is the definition of a larger ionization energy.